We are going to start by looking at how light reflects off of a plane mirror or a flat mirror. All rays of light emanating from the top of the object are going to head directly to the mirror and follow the law of reflection in bouncing off of the mirror. Let's draw some in. This first one that I am drawing goes in, and it's a special case where the ray hits and lies directly along the normal. If it lies directly along the normal, then the angle of incidence is 0 and the angle of reflection will also be 0. So the light bounces back straight on the path that it came in on. This next one, we're going to send in at an angle, and it will hit the mirror and it will follow the law of reflection. So the angle of incidence has to equal the angle of reflection. Okay, now I'm going to draw another one just to show it doesn't have to be the ones that were pre-drawn on this figure. I'm going to draw a beam of light going from the top of the object to the mirror, and I'm going to follow the law of reflection. So angle of incidence has to equal the angle of reflection. Now let's look at those 3 reflected rays of light that I drew. Are they ever going to meet? No, they won't. So we're going to need to extrapolate them back behind the mirror. So I'm extrapolating all 3 back behind the mirror with dashed lines, and the figure shows them perfectly meeting, but I'm going to show that we don't really know until we extrapolate them back. Wherever they meet is the top of the image, which is mapped from the top of the object. From this, we can get the image height. And finally, I'd like to note that DO is the distance of the object to the mirror, and DI is the distance of the image to the mirror. DI is negative because it is behind the mirror. Now let's look at a more involved situation where I have 2 flat mirrors or 2 plane mirrors that are at a 90-degree angle with respect to each other. We are going to start at the object and draw a ray of light to hit the first mirror. Then we will follow the law of reflection. Angle of incidence has to equal angle of reflection to figure out at what angle our reflected ray is going to bounce off of the first mirror and head towards the second mirror. Now at the second mirror, we'll do the same procedure. We'll draw the normal. Angle of incidence equals angle of reflection, and I will draw my reflected ray off of the second mirror. Same procedure with the other ray that is in the figure. These 2 rays aren't ever going to cross. So I will again need to extrapolate them back in order to determine the location of my image. Where they cross is my image location. Let's extrapolate the rays back for the second mirror. And again, where they cross is the location of the image. The image labeled I1 is the image that is created from the object reflecting in mirror 1. The image labeled I2 is a reflection of the object in mirror 2. It does not have the rays drawn on the figure for it. The image labeled I3 is a double reflection of the object first off of mirror 1 and then off of mirror 2. We will now turn our attention to spherical mirrors or curved mirrors. Recall in the last video, I explained that these mirrors are just a small section of a giant imaginary sphere, and the mirroring can be on the outside of the sphere or the inside of the sphere. Now let's look at what happens when light reflects off of a concave mirror. Notice some of the labels in this figure. C stands for center of curvature. That's the center of the big imaginary sphere that this mirror was cut from. R is the radius of curvature, the distance from the mirror to the center. And the principal axis goes from the mirror to the center of curvature. We are going to think about a light ray coming in and hitting the mirror and being reflected. Since this mirror is curved, I'm going to first draw the tangent to the mirror at the point where the ray of light hits, and then I'm going to draw the normal that is perpendicular to that tangent. Next, I'll follow the law of reflection, that the angle of incidence has to equal the angle of reflection. This tells me where to draw my reflected ray. Now, we will do the same thing with a convex mirror to understand how light gets reflected off of it. Notice we still have a principal axis. C is the center of curvature. That's the center of that big imaginary sphere that this mirror was taken from. And R is the distance from the mirror to the center of curvature, and it's called the radius of curvature. First, I draw my incoming ray. Now I'm going to look at where the ray hits the mirror and draw the tangent to the mirror at that location, and then draw the normal to the tangent. I'm going to follow the law of reflection. The angle of incidence equals the angle of reflection, and use that to determine how to draw my reflected ray. Now we're going to go into more details on a concave mirror example. We're going to start with an object of known height that is a known distance, DO, in front of the mirror. So it's going to be a positive DO. C is the center of curvature, and V is the vertex. We're going to start by drawing a ray that starts from the top of the object and goes to the mirror. Where the ray impacts the mirror, we will draw the tangent to the curved mirror. Then we'll draw the normal. Using the normal, we will figure out what the angle of incidence is and the angle of reflection. That allows me to draw my reflected ray. Let's do the other one in this diagram. The ray goes in. Where the ray meets the mirror, I draw the tangent, and then I draw the normal to that tangent line. This is a special case. The incoming ray lies directly on the normal. That means the incident angle is 0, therefore the reflected ray will also have an angle of 0 compared to the normal, so the ray will just bounce back on itself. Let's do one more to show a ray that wasn't pre-drawn on the figure. Where the incoming ray meets the mirror, I draw the tangent and then the normal. Using the normal, I apply the law of reflection, having the angle of incidence equal the angle of reflection so that I can draw the reflected ray. Where the reflected rays meet is the top of my image. So the top of my image has been mapped from the top of my object. I can see that in this case, the height of the image is a smaller magnitude than the height of the object, and the image is upside down or inverted. DI is the distance from the image to the mirror, which in this case is positive because it's in front of the mirror. That was a concave mirror with the object further than the center of curvature. Now let's look at an example of a concave mirror with the object closer to the mirror than the focal length. Here is my object. You can see that it is closer to the mirror than the focal length. We're going to use the same procedure of drawing rays from the top of the object towards the mirror and applying the law of reflection. This first ray is the special case where the angle of incidence is 0 because the incoming ray lies directly on the normal, so the ray will bounce off upon itself. We're going to do the next 2 rays the same way. Starting from the top of the object, we'll draw towards the mirror, we'll draw a tangent, a normal, and apply the law of reflection to determine the direction of the reflected ray. Where those rays meet will be the mapped top of the image from the top of our object. But wait, those rays aren't going to meet. We are going to need to extrapolate them back behind the mirror to locate where they meet. Okay, now where they meet is the top of the image. This is another example of a concave mirror with a distant object. I have my object, which is very far away from my mirror. It is beyond the center of curvature. Same procedure as before. Incoming ray, where it hits the mirror, tangent, normal. Use the normal to get the outgoing ray by using the law of reflection. Let's do the other 2 rays that are shown in the figure. Since all 3 rays started at the top of the object, where they cross is the top of the image. This example shows a convex mirror with an object that is in front of the mirror. So DO here is a positive number. I'm going to draw my incoming ray. Where that ray meets the mirror, I draw the tangent to the mirror at that point, and then I draw the normal line that is perpendicular to the tangent. Then I use the law of reflection to draw my reflected ray. Let's draw the next one that's on the figure, and that's that special case again where the ray gets reflected back upon itself because the incoming ray lies directly on the normal line. Next, we look for where those 2 reflected rays of light are going to meet. And they're not going to meet, so we need to extrapolate back behind the mirror. Where those 2 extrapolated back rays meet, that is the top of my image. DO is the distance from the object to the mirror, and it is positive because it is in front of the mirror. DI is the distance from the image to the mirror, and because it is in back of the mirror, it is negative. Let's do a quick recap. When we have an object that is up close to a concave mirror, it makes an image that is behind the mirror and magnified. Since it is behind the mirror, DI will be negative and the image will be classified as virtual. A practical example of this kind of mirror is a shaving mirror or a makeup mirror, where we are the object and we're up close to the mirror, and what we get is a magnified image. All right, same type of mirror, it's concave again, but when we move our object very far away, so further than the center of curvature, what we get is an image that's quite different. This produces an image that is in front of the mirror, inverted, and smaller. So because it is in front of the mirror, the distance from the image to the mirror is positive, and the image is real. You can actually take a household shaving mirror or makeup mirror and get very far away from it, and you will see your own image become upside down. Finally, we also looked at convex mirrors, and they make images that are smaller than the object and always closer to the mirror than the object is. They are also upright. An example of this is the passenger side view mirror on a vehicle. Those side view mirrors are convex, and they have printed on them, "Objects in mirror are closer than they appear." We use these mirrors because they give us a bigger view of the road behind us. But the trade-off is that the objects in reality are closer to the car than they appear, because the image produced by a convex lens is always smaller than the actual object. This shows a plane mirror. The bottom duck and whale are the objects, and the top duck and whale are the images. Make note of the size of the images. All right, I've flipped the mirror and now have a concave mirror showing on my duck and whale. And look at the size of the images now. The bottom are the actual objects, and the ones that are on top of this video show the images. And the images are substantially larger than they were in the plane mirror.